Okay, so just start. So today, oops. So today we will do a new lab. So this lab, so we will do RL and RC circuits. Okay, so now we will do inductor and capacitor in AC circuits. Okay. So for today, we will use these two equations. Okay. So XL equals 2 pi FL. Okay. XC equals 1 over 2 pi FC. Then actually, so this one we don't use, and this one we will use. We used these formulas last week, right? So VRMS equals 0.707 VM. And VPP peak to peak value equals 2 VM, 2 times of the VM magnitude. Okay, so circuit is not difficult. So for this one, so AC source, AC voltage source, 100 Hertz. Then connect to resistor RS, this for sensory, okay. Then capacitor, so they are in series. So this is a series circuit. So capacitor, so 1 mu F. The same as the last one, we need to adjust the voltage, the source voltage, until VC equals 4 volt peak to peak. Okay. Then we need to measure VRS. So again, so in the real lab, we will use the multimeter, digital multimeter, measure this value, and that get is the RMS value. So it's different. Then in the ThinkTech, we know we can only use the oscilloscope, measure the peak to peak value here, peak to peak value. Okay. Okay, so we can start now. I already create this in the Tinkercad. Okay, then after finish this one, so I will post the link in the Canvas. So first one, breadboard. And AC voltage source, so we need to change this to O. So function generator. Okay, so maybe here. Then make this smaller. Keep smaller. Okay, so this a little bit small. Okay, let me zoom in a little bit. Okay, so first one, 100 Hertz. So 100 voltage, actually we don't know. Offset 0. Then sine wave, so sine. Then for the power, like we did before, so positive, then connect positive to positive, then negative, then negative to negative. Okay. So this is the source. Then the last one, 100 ohm resistor. So one resistor. Okay. Yeah, I could. Yeah, I could. So 100. So change to ohm. So use the right number again. So don't use the nominal value. Yeah, use this number 102.8. So if you use nominal values, everything just every number should be just the ideal number. Okay, we cannot get any difference. Okay. So use this number. Then the last one, capacitor. Okay, So capacitor, you could use this one or this polarized. Polarized, just remember polarized, this one has the ellipse, yeah. The leg has the positive and the negative. So this is the negative, this is the positive. So we need to flip, mirror this one. So this should be positive, then connect to the resistor. So maybe let me go here. Let me, yeah, go to this place. Go up a little bit. Okay, so this means I need to connect this, right? Then from here, this one I cannot see, moved it. So this goes to negative, go back. This change to green. Then this one, so connect to the positive, okay. So this is the whole process. So the current out from the positive through green line, through resistor, then through capacitor, then ground, ground, ground. So back to the negative of the source. Then the last one, so we know just like the last slide. So we need two oscilloscope. Okay, change it to red first. So one oscilloscope measure the voltage across the resistor, so 100 ohm. So we can go here. Then this is actually negative. So oscilloscope across the resistor. Again, I said before, only in simulation we can do this way. Okay, so this one can go just go to the ground, because for the capacitor, this lead connect to the ground, right? Then this go here. So this is the positive. Okay, so now we can start the simulation. So this is 100 Hertz. So first one, change the time setting here. Maybe go to 100. This too large. Let's try 1. Okay, 1 is good. Then this also 1. So 1 millisecond. Let me stop. And okay. Oh, something wrong. What's wrong? Inversed. Positive. Negative. Yeah, correct. Let me stop. Delete this line first. Alright. So now this is correct. Oh, no, still something wrong. This is inversely polarized. So weird. This is positive, correct? Okay, so let me double check. So this one, positive, positive, positive. Yeah, this is positive, correct? Positive, negative, negative, negative. Yeah, everything seems correct. This is 100. Yeah, correct. Let me double check this. Okay, let me rotate this. Then flip again. Go down this one. So this positive, this negative, Mm, everything seems correct. Why is that is not correct? Capacitor inverse polarized. It's weird. Okay. Let me flip this. Oh, I delete. Stewed error. Yeah. Maybe this one is too large. Let me change this to 2. The same. Okay, so let me use another one. This one, I don't know whether I can use the 1 mil. Actually, usually disk ones doesn't have this so large. Okay, rotate. This one doesn't has the polarization. Okay, so I need to connect this. Green. This is correct. Oh, I did wrong. This is the negative. This is the, but this is not about the, so this is, let me double check, but I didn't connect this. Okay, run again. Still has something wrong. You can see, yeah, this curve is curly, it's weird. Okay, let me go back to this one. Let me double check. Okay, just double check. So actually, I think I did this in ThinkTex, yeah, several years ago. This one doesn't matter. Oh, the same. Positive, 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 negative, negative. It's so weird. Okay, so let's just keep doing this. Just use disk one. Let me check what's wrong. Oh, I will check this later. Yeah. Let me double check function generator, sine wave, 100 Hertz. Yeah, correct. Maybe because the simulator, the function generator, maybe 100 Hertz is too low for this function generator. Okay, that's okay. Just start simulation. So again, so we need to adjust the source voltage until this is the 4 volt. So VC equals 4 volt peak to peak value. So you can see now the setting for oscilloscope, the right one is 4 volt from top to the bottom. So this means we need to increase the source voltage. So let me try 4 first. Not. Okay, it is. Okay. So this one almost 4. So now it's 10 volt. So from top to bottom. So now we know this is just 1, right? 1 volt per division. So this is almost 4. So actually we could just a little bit, maybe try 4.2. Okay, I think 4.2 is okay. Then, so now this is the 4. Okay, so 4 volt peak to peak value for the capacitor. Then for this one, the setting here is the 400 millivolt. So we know from top to bottom. Then each division, so it's the 40 millivolt, 40 millivolt. Then we can count. This may be 4.2. No, sorry, 0.2. So 1.2, 2.2, 3.2, then 4.2, 5.2, 6.2, another 0.2, maybe 6.4. So then VRS, so we know this is peak to peak value equals 6.4 division times 40 millivolt per division. Then this one, so we know is 256 millivolt. So then this one, so we get the VC peak to peak. So actually here, didn't, yes, set this one. So yeah, maybe you can write down here. Just remember, so no, this is not VC. Okay, so this is not VC. This is VRS. Okay. Okay, so this is VRS peak to peak value. Then for this one, we know. So for the VRS, DMM, in real lab, we will get the multimeter. But here, so we need to get from the calculation. So VRS, this is RMS value. So actually it's RMS value. So it's the VRS peak to peak value. First one divided by 2, then you get the magnitude. Then keep divided by square root of 2, then you will get the number. This is RMS value. Then you will write down the number in this position. So VRS. Okay. Then for the I peak to peak, so we know this is from the Ohm's law we did last week. So I peak to peak, so that's the VRS peak to peak value divided by RS. So again, here you need to use the measured value, 102.8. Oh, okay. So use this one, get the peak I current peak to peak value. Then the last one, so after get the current, so you can use this formula, get the reactance, XC. So XC, so it's VC peak to peak value, so we know it's 4. So this is 4 divided by current. Then you get the XC. So it's put in here. This is a calculated value. The measured value XC, this one, so actually is this formula. So XC equals 1 over 2 pi FC. So here XC should be a large number, okay, because capacitor is very low, just 1 mil, 1 microfarad. Okay. Frequency is also low. Okay, so this one, yeah. Then other formulas, yeah, so just get this. Okay. Then in this one, the step G, so you can see collect a 0.47 mu F in parallel with the capacitor, this one, the 1 mu. Okay. So for the parallel, so if we use this one, okay, let me stop simulation. So first, for parallel capacitor, so you need to use this formula, get the total capacitance. So CT equals C1 plus C2. So here we need one more at here. So now these two are in parallel. So this now we need 0.47. Let me double check. Yeah, 0.47. This is the one. Yeah, this is the one. So run simulation again. So not changing much, but this one changed. So RS changed. So you can see then the setting, this is the 1 volt from top to the bottom. So this means each dimension is just 0.1 volts. 0.1 volts. So then this one from top to the bottom. So 1, 2, 3, 4. So almost 4 dB. 4 divisions. So that's the 0.4 volts. Then the same process. So you can get the current. Then get another new XC. Okay. Then also compare with the nominal value. So we know get total capacitance first, then use this formula, get the XC. So this is the measured value. Then compare with the value, the calculated value from the Ohm's law. Okay. So this is the whole process. Okay. Then the last one, similarly, so this is the RL circuit. So just change this to inductor. So 10 mil Henry. So this one, this is the inductor. 10. Okay, so you can also change this. So this is 10 milli Henry. So very large one. Okay, let me erase this first. So the same process, the frequency now is the 2 kilohertz. Don't forget this one, 2 kilohertz. Adjust the source voltage until the VL is 1 volt peak to peak value. So peak to peak value. Then measured VRS. So in ThinkTech again, so we can get this directly from the oscilloscope. Then from the calculation, so we can get VRS. The same process, get the current, then get the XL. So this is calculated value, then compare with the measured value. Measured value use nominal value here, then XL equals P 2 pi FL. So 2 pi FL. So this is the measured value. Okay, L, so just use the 10 millihenry. 10 millihenry. Okay. Then finish this calculation. Then the last one. So we also need to add one more. Yeah, here. So connect the second 10 millihenry coil in series. So this is in series. Then, yeah, check everything again. Okay, like this. Okay, so this is the whole process. Okay, so first the RC circuits, then RL circuits. Okay, so hopefully you could finish, yeah, this. today or by last Thursday. Okay, so now I can, yeah, stop recording.